wanted just to kind of maybe start with asking Brigitte, what problem is, space solar uniquely addressing? And so what got you to work with these three musketeers? And I have to say, we French, the three musketeers were four. Everybody knows that. So maybe you are the fourth musketeer, the D'Artagnan of solar power by space solar power. So
So this really started about 14 years ago, where my husband was looking to do something really meaningful and have an impact. And he thought now is the time for space-based solar energy because it's the next frontier and of clean, abundant, and reliable energy. And we went to Caltech because of JPL, the relationship, because we figured, if we could be having rovers on Mars, why can't we do this? So it took a few years, but eventually Harry, Ollie, and Sergio rose with a wonderful and viable pathway to make this happen. And this has been this journey. And the important part, and this is really important because the premise of their proof of concept was always based on making the cost of electricity equivalent to what we're currently paying on Earth, because that's the only way we could scale this up so it can serve humanity. And that was a very important part of it. And somewhere along the journey, maybe 2-3 years into the research, I had a lunch with them and they were giving me an update. And it's just, you have that moment in life where and I was like, they're going to do it. And so that's when I called Steve. And I thought we have to get this on film to get the different stages, because this is going to be history.
Yeah, so our good segue, thank you, to Steve. So tell us about the documentary.
Well, I had lunch with these guys, and they were completing each other's sentences. And I thought, oh my gosh, these are not only are they great scientists, they're perfect for a film. And if we never got to know them, it's really fun hanging out with them. So what we did is, over several years, we filmed them as they were leading up to this launch and everything else. And honestly, it was really awesome. So to answer your question, why a documentary? Because I think it's a really good way to visually see where how all this works. And they can explain even better how it works now, because I'm done.
Okay, so thank you very much. On the technical side, from a technical and efficiency standpoint, so what are the breakthroughs that really made that possible?
I could go ahead and say, first question you should ask is, why are we doing this? Well, obviously for engineering faculty at Caltech, it's because it's a really cool idea. But what's the transformational ideas? I think there are 3 transformational ideas. One is just like solar power on Earth. This is modular and scalable to an enormous scale. It can be very cheap, and that's one of the things that we've really worked on. The other thing is this enables baseload solar power, like a nuclear power station. It's always noon on a sunny day in space. Third, as Ollie will tell you about, this enables a wireless grid. This allows you to beam power anywhere on Earth to a place where there is not already a copper wire grid. And we can reconfigure. So for example, suppose you need not a constant output of power, but you need power in Houston and not power in San Francisco. You can actually redirect the beam and follow the grid. So this is really quite transformational. So the question is, how do we do it? And that's what we have been involved in.
Yeah, and to follow up on that, a couple of interesting things, since we are in the business and management side of things, important to know a couple of numbers. So the first question I ask myself is that why you want to put the solar panels in space and not on Earth, right? Because you could put them on Mojave Desert and then say, well, done it. The problem is that there's day and night, clouds and everything. And when you count all of that, depending on which city you compare it to, you get a factor of 15, or 12 for London or 5 for Mojave. So on average, about 8 times more energy. Now, you asked about the efficiency question. That's another interesting thing. Yes, the efficiency of transfer is not 100%, but when you add it all up, and we've done this in a paper that we published, it's a Jewel paper, that's an actually techno-economical analysis that may be valuable to people, is that with that factor of 8, when you look at the equivalent efficiency of photovoltaics on Earth versus in space, you get actually about a factor of 2 higher. So basically, you get about equivalent of 40% overall efficiency compared to 20% on Earth because of that factor of 8 more energy accessible. That on top of that, you also have all of this dispatchable energy where you can set it where you need, when you need them, as much as you need.
Just a dumb question. So the clouds are not hampering the transmission.
No, that's a great question, actually. So the frequency we've chosen, that the atmosphere of a cloud loss are 1 or 2% of the total energy on a cloudy state.
And there is another side to the efficiency question, and that is the cost of launch of anything into space, which has been decreasing, but on the whole is still expensive. And then, okay, what is the mass of the system that we're going to put into orbit? And there is a kind of, space technology is very mature in many areas, for example, in solar arrays. And when we started to look at solar arrays, if you like, with a critical eye, it turns out that because of the need to protect the photovoltaics from radiation in space, actually most of the material that's being launched is glass that is protecting the photovoltaics. So a huge amount of effort has been into removing that glass, not just making it thin, but simply removing it. And when you go to the limits of, as it were, radiation hardness, where are the limits? And so that is the purpose of the demo that Harry was doing, when he said, we are testing some materials that have never been tested in space. Now, the next thing is that the structures that Ali studies, phased arrays. Phased arrays are normally built on sandwich panels. Well, they weigh 1, 2, 3 kilograms per square meter. Well, we are not going to do that. So we did some incredibly lightweight substrates, which nobody had ever done and nobody had ever thought about. So you kind of attack this kind of a mass efficiency question kind of at all spots. And he said, well, where do we end up? And the answer is about 100 grams per bit squared. So this structure is extremely lightweight. Of course, it's still massive because it's huge. But then in this way, we are able to look at, in a new way, at the cost of launching giant space infrastructure. And that he fed into the study, the techno-economic analysis that Ali was telling you about, where we kind of looked at all the numbers. And it turns out that the launch cost is actually not the largest. The largest cost is actually the cost of building all these sheets that we have to put into space.
And if I may put that number in perspective very briefly, 100 grams per square meter is the weight density of a sheet of paper, a standard sheet of paper, in terms of the mass density to get a feel.
I see what you were saying, Stephen. Like you work together very well, and you're kind of on the roll. We don't even need to ask you questions. But then my question about this, about the complementarity. So you're saying, in the documentary, we see some of that the fact that you could work together is really important. That each would bring a piece that was necessary for the system to work. Can you elaborate a bit on this?
Yeah, well, I think I've worked on solar power my entire career, ever since I was a graduate student back, more than 40 years ago. But even though I'm an electrical engineer, the sophistication that Ali and the lead technology that he brings is unparalleled, and the kind of things that Sergio does, these origami-like or kirigami-like structures, you won't find almost any other place on Earth. So it was a really serendipitous combination.
Just to give you a little more background about how we came about it. We started working on communication system and radar, things that led to, just a couple decades ago, to research that led to automotive radar and 5G and 6G today. But we saw that this technology has potential. First, we were thinking about only terrestrial application, which is still ongoing and active for charging devices and valuable power available to different devices. But then the opportunity emerged that you could actually create this in a scalable fashion that's manufacturable, because that's another aspect of these things. I mean, any thing requires a reasonable level of understanding of operations, and that the sooner you think about that in the process of design, the better off you are. Because if a lot of times people develop things and they go far, but they're not scalable into manufacturing. So the operational side of it was something that was on all of our minds from day one, which allowed us to make it scalable.
And another side of that is that large engineering projects, the way they traditionally happen is that there are specialist teams and they do their thing and these pieces come together. Whereas what you have seen through the documentary, and I think this discussion also is beginning to show, is the way we work together. So that means that different disciplines have not predetermined ahead of time the limits of one piece and another piece and another piece. Now, I have done many projects with space agencies, companies, and so on, where the specialists are doing their thing, and finally the whole product gets put together. And there is an enormous inefficiency in that, even though it's easier to kind of schedule the tasks. So this is now, if you like, what you can do in a university and environment, and maybe quite difficult to do in large companies. And maybe it's just the way in which we want to develop technology, kind of this thing about integration. Integration needs to be kind of running through the whole process. And I mean, the more as we think about future systems, this is not just space solar power, but aircraft, anything. The more we think about integration and the more the limits, the cost, performance of the systems can be substantially transformed.
So, I mean, to build on what you're saying about scalability. So what are the next steps in terms of where are you going in terms of commercialization? We had the previous panel, which was all about, is there demand for that? So where are you in the process and where are your next steps?
So one thing I can say is that the other place where you can bring together a small team that can change the world, just as Margaret Mead advised, is in an early stage company, and that's really the next destination. I would say the work is that we do at Caltech. There are many very challenging problems that are still need to be addressed, but to really build and de-risk to the point we were able to fortunately to be able to do a first demonstration in space, but to really start building things that are look like products that people want to buy. This is, of course, what you study here at UCLA Anderson. So we have a revolutionary technology. There's exploding demand for all things in space. The number of spacecraft that have been launched per year gone up by orders of magnitude. So the needs for power, in space, the needs for power, powering things from space, communications, power systems. These are, we think, really important stepping stones to going all the way to the vision of space solar.
And the scalability, as Harry pointed out a few times, on a couple of different things. There are still technical challenges of scaling that we're addressing and working on, or the research was. But in the past life, I've also had the opportunity to start companies that took something from research and take it to actual production in large volumes. And one of the important things in that landscape is the ability to move ahead of the curve in the sense that anticipate all the issues and build for scaling. So the startups is the pathway we are reviewing it. And what I see is some sort of equivalent of a Moore's law for this technology and space technologies, in the sense that the way Moore's law was more a prediction and a roadmap than just a prediction, right? Because it basically, once it was declared and everyone agreed with it, then everyone tried to stay on it, which basically instigated more effort and activity to make it happen. So it became a self-fulfilling prophecy. And there is a Moore's law of scaling space structures, which I think is best addressed in conjunction between the research that continues to be done to enable these and overcome fundamental problems, as well as the commercial side and the startup enterprise.
And just one final point about, as you were, next steps. We've been thinking this past several months about, okay, this startup that we're going to do, in which area we're going to focus. Because, the tendency would be to do the whole thing that you have described. That it's just huge. And the market doesn't exist. And our technology involves so many components. So after months and months of discussion, finally we decided is that we will focus on the extremely lightweight photovoltaics, coilable, and if you start producing and selling some new kind of solar arrays with which you can actually power spacecraft of all kinds. And then we're thinking that that is the way in which we're going to try and make real products and gradually scale up, but also, in fact, advance the technology that is then connected to all the rest, because all these pieces are integrated.
I'd like to add something to this. So to get a higher view of how we could get this done, it's a hybrid approach. And first of all, we need policymakers and economists, because they're the ones that are going to make the argument this is needed now, because they're going to translate a technological breakthrough into national interest, climate mitigation, national security. I mean, all of the things you'd want. And the economists, of course, they're going to calculate the cost curves and all of those things. But what you really want them to do is to quantify the benefits that the market has not been able to price yet. So those players are very important, and I have to move it alongside as the technologists. But also, when you think about how do we finance this? So that's the approach is really, you need government. So I would hope that our government would fund the deployment and the pilot system. And they should be the first anchor customer for the big picture, because defense needs it. I mean, we have grid resilience issues. I mean, there could be a disaster response. So the energy is needed for that. And then at the next level, there's VC. So venture capital money is really essential for the component parts. So it would be the ultra-weight solar voltaic cells. It would be for, different hardware for the wireless communication transfer. And then you go to private equity. Now, private equity should only come in once, we have offsets and the pilot systems are set. And they can then come in and finance the first commercial scalable system on Earth. And so I think we just need all of these players to make it happen. I mean, all the while you're perfecting, the systems for Earth, and in the meantime, powering space for all of its needs, including data centers, which from the previous panel, I think that would be terrific.
Yeah, well, thank you. I think, I think it's kind of an interesting, combination, and what you're providing here is a really clear path on where this could go. And my question is also, in all of these technologies we've been talking about, there will be some resistance. So nuclear, there's resistance, wind, there's resistance. What do you see some of these resistance that people could, kind of put against that?
The first question, I'm surprised that we haven't got this already, is how do you show that it isn't a weapon, or as we call the smoking bird problem? So one of the things that you can show with laws of diffraction is that if I have a structure with a certain wavelength and a certain size, the energy density that I can form in the beam, I can guarantee from the physics will be safe. And the space solar power system that our architecture is designed to build is one that produces solar power with a power density that's similar to that of sunlight. So what you can envision is, suppose you have a utility solar installation like you have in San Luis Obispo County or in Nevada, and you have a large field. It's a secure facility. It's grid connected. That facility can receive terrestrial solar power in the daytime, and of course, then it power has to be provided some other source at nighttime. But it can receive space solar power 24 hours a day. And so you can think about the same facility. The antenna receiver array can actually be made to be substantially transparent. So you could imagine putting this actually on top of photovoltaic panels and installations that already exist, and actually co-locating the infrastructure so that power that is at a safe level can be received efficiently and then tied into the grid in using infrastructure that we already have today.
And to add to that, the primary question, what I call the Death Star question. There. So the other question is about like the challenges about the orbits, because as the space technologies and companies are emerging more and more and becoming more popular, there are a lot of launches in low Earth orbit and also geostationary orbit, and the demand for orbit and this question of space junk and all of those things. So those questions are interesting because we've been looking at those, and some of the technologies we develop, which we didn't talk about. For example, there are these what we call transmit arrays that are like flying in MEO. They can fly in thin LEO and GEO, and that they can redirect the energy, and that allows the system both to become a lot smaller, but as well as the fact that it works in orbits that are not as crowded, and reduce the risk of space junk and all of those aspects. So the system, once it's scaled properly, can deal with all of these aspects in that regard, which are valid questions in terms of the crowd, how crowded these orbits are getting.
Okay, well, I think this is all a fascinating discussion, and I just wanted to ask also Steven. I mean, there's this documentary, Bright Harvest, that you are showing in festival. So, what are the next steps in terms of this, roadshow to explain the technology, the advantages, and all of that? So,
we've entered into festivals. We're also screening this at universities and places like this to really get awareness out. And I can't think of a better way to sell this than on a film like this, and you can actually get to personally see these people when they're not there.
right, yeah. Well,
And I'm also viewing the film as a vehicle because we really are at a point where we need government support. So I'm taking it to DC and trying to get that moving. And I have to say, I was there a week ago, and the people I spoke to were very receptive. So I'm hopeful.
oh, great news. So thank you very much to the panel, and we will have a few minutes. We are after that breaking out in different groups, so you have an opportunity to talk to the panelists. And again, thank you very much for coming, Ms. Gilser.